Hello everybody, welcome back to our MSE100 where we've been looking at essentially we've been building up Hello everybody, welcome back to our MSE100 lecture series on engineering drawing and also using essentially computer aided drawing. So here today's lecture what we've been doing so far is we've been looking at essentially creating parts in SolidWorks, and then we looked at adding dimensions in SolidWorks, and then we looked at dimensional tolerance, which is basically if you have a size, so you have a variation in the size, you were applying some limit or a tolerance on that dimension. So what we're going to be doing is looking at another aspect. So you have a size, which is kind of how long a part is, and then you also have a shape, right? So instead of this ruler being straight, you could have it twist this way, kind of twist one way or the other. That affects the shape. Similarly, if you think about actually designing a cylinder, you can have the cylinder kind of like warp all over the place. The cross section may not actually be circular. So all of that are actually the geometric features of that particular part. And then what we're going to be doing now is looking at applying the similar tolerance that we had on the dimension to applying kind of like a tolerance or a variation on the geometry, which is where the name geometric tolerance comes from. So that's our learning objective. So we are going to be comprehending geometric tolerance. So where we will do some few exercises. So we'll kind of do a quick review of our dimensional tolerance, and then we look at why is it that we need geometric tolerance, and then we will kind of continue and then apply essentially kind of like do some exercises in geometric tolerance, and then we'll summarize the video. So let's look at a quick review of the tolerancing concept. We'll just capture the important details over here. So essentially the idea behind geometric tolerance is essentially when you want to increase the accuracy of a part, you need to spend more amount of money. So essentially your accuracy comes at an increased cost, and it depends on your design intent. For instance, if I'm making the shirt off by a couple of even like half an inch or a couple of centimeters, it's not that big of a deal. But then if you're basically looking at an assembly of a door, so maybe you want to make sure that the door is smaller than the opening. You can always fit it, so you don't want it to be larger. So then you have a different tolerance trade-off that goes in here. Nonetheless, as designers, you would have an idea what is it that you actually want to do. So typically, because you're not going to be manufacturing the part as well, and then you don't want to kind of like constantly go back and look at all your notes about the application, what you would rather do is convey all of those information in a standard drawing format. So that's where the tolerancing comes in. So in keeping with that, so we keep our design intent in mind, and then we pick an acceptable tolerance. We looked at two main types of tolerance. So the first one was a symmetric tolerance, where you had it of the form 10 plus minus 0.1, where you can kind of like go up and down by 0.1. In this case, it's millimeters. And then we did bilateral tolerance, where you can basically the same dimension would be 10, and in the bottom you have minus 0.1, and in the top you have plus 0.1. So this basically is the same concept. So the advantage here is I can actually have this bilateral tolerance need not be symmetric. For instance, if I'm dimensioning the door, so I might say, okay, you know what, I can make it a little bit smaller, but obviously if I make it larger, obviously this might be a doll door. If I make it larger than 10 millimeters, then the door is going to get stuck in the opening. So I can take that into account when I'm applying the dimension. Just a quick recap. So what we did was we kind of assumed that we're going to be doing about 1% tolerance and then rounding it off the nearest point, 0, 1, 0, 5, and so on and so forth. So this again is not a standard convention, but we're going to be following just to kind of like make things more interesting. And so when we are actually creating the dimension, there is a concept of tolerancing stack up, where dimension tolerance on variation 1, then you have a second variation, so the overall variation is going to be a little bit larger or small. That's where the concept of tolerancing comes in. So this is what we have done so far in the previous video. So let's try to see essentially applying the dimensional tolerance to our what actually happens in the case of a dimensional tolerance, and what is it that we're actually looking at. So let's look at this example over here. So what I've done is I've actually drawn a bunch of essentially rectangles. They are kind of like dimensioned to be 10 or rather 100 millimeters plus minus 10 millimeters. So obviously I just made it a little bit larger so you can actually use a ruler to measure all of these values. So what you're going to be doing is you're going to measure all of these and then let me know. So if you can number these from 1 to 5 over here on this page. So we're going to basically look at this and then see whether or not these are going to be accepted. So I'd request you to kind of like pause the video here and then do this and then return back to the video. So I'm going to be a little bit lazy. So what I'm going to do is I've actually measured this out. So I'm going to draw a line essentially at 90 millimeters from this end over here. So from this end, all of the lines, because they start at the same point, I'm drawing one line at 90 millimeters and then I'm drawing another one at 110 millimeters. So obviously if you look at the very first one, that is too short. That's not going to be good. So the second one is just about acceptable. So it's touching 90 millimeters. So again, based on how you measure it, it might turn out to be just a little bit too short. That's okay. So then the third one is good. Fourth one is just acceptable on the high side, and the fifth one is too long. So I'm just going to extend these lines a little bit further down into the page. So I'm going to go to the bottom page, and then let's look at the third part, like another part over here. So it should be part number 6. So where basically, so this one is a little bit longer, but one of the edges basically goes longer. And then let's look at another one where the far edge is not straight, but it's kind of still within bounds over here. And then finally look at one which is kind of like wiggling all over the place. So the question then becomes, is this an acceptable? Which ones are going to be acceptable? So if you actually look at your tolerance specification, what is it that you're saying? Right? So you're basically saying, I'm going to accept all parts with between 90 and 110 millimeters. That's what your tolerance spec says. So then the question is, are you able to accept these parts or not? So if you think about it, because you only conveyed the information regarding the dimensional tolerance, what that means is you're forced to only reject, or rather, you have the option of only rejecting the first one, because you can say, hey, you know what, this edge is beyond, so I don't like this part. But then these two are actually well within your dimensional tolerance. So what we need to do is we need to kind of like think about the shape of this tolerance. So before we actually proceed to the geometric tolerance, I just want to note that when we talk about geometric tolerance, because your shape could kind of warp the part up, particularly if it's non-uniform. So all of these tolerances are actually enforced at room temperature, so the normal room temperature. So there is, and then typically there is no load condition, which is known as the free state. So if it's an assembly, then you have to figure that part out. So that's what we're doing in this case. So let's look at the next page. So let's just answer a few questions, right? So the first question is what we mean actually by dimensional tolerance. So the dimensional tolerance is essentially a tolerance or a leeway that's applied to the size of the object. So essentially kind of either the diameter, or you can have the length, width, what have you. So then the question is, can I actually control, in the previous example, can I actually control the shape, or kind of if you think about the previous object in the previous page, so can I control the waviness of the far edge using the dimensional tolerance? So you could potentially do that. So what you can do is you can set a very, very tight dimensional tolerance. So if I made the dimensional tolerance say basically 10 to the minus 3, which is a very, very small tolerance, then you can kind of ensure that the waviness is much smaller. So essentially what you're doing is you're shrinking the allowable range over here. So what is that going to happen? So typically, this might be an overkill. So the reason is you can potentially have the part at 90 millimeters, but you might only be concerned with the waviness of the far end. So then you can basically potentially use a 90 millimeter part, which might still be acceptable in your particular application. Again, it depends on your application as long as the end is flat. But then if you kind of enforce the much stricter dimensional tolerance, what you're going to do is you're going to significantly increase the cost, right? So what will happen is you're basically going to make it much more expensive. So this is where the geometric tolerance comes in, because you would be able to control the length of the part in one tolerance. So you basically provide that information, and then the waviness of the part, or the more specifically the geometry of the part, could potentially be controlled to a tighter tolerance, and that's where the geometric tolerance comes in. So G, D, and T. So that's obviously it's going to be more important when you're talking about, or in the context of the assembly. So what do we mean by that? Is, so for instance, if you have, say, a part, and then so imagine the hole is about 12 millimeters, and then you kind of like try to assemble. So this is actually a bolt which is 10 millimeters. So obviously you would think that there is enough clearance so the bolt will go through. But if one of the holes at the bottom, so for instance on the right over here, so if this hole is not straight, so what's going to happen is this the bolt is going to hit on the corner, even though it's 10 millimeters, because of the way the geometry not being straight, that's going to cause a problem. So keep in mind, it's not just that this hole being incorrect. So you can also have an issue where you can cause stress in the bolt, where if this surface that are mating aren't compatible. So you could cause the same problem in different ways. Similarly, this bolt could also not be straight, so that will again cause the same kind of a geometric problem. So that's where this comes in. So the current GD&T, so basically GD&T ASME, GD&T ISO standards. So there's a little bit variation on how this actually came about. So one of the stories I've heard is that during the World War II, when they're shipping parts using only the dimensional tolerance, they found that when parts weren't quite interchangeable because they had issues with the geometry. So that's when I think it was somebody by the name of Mr. Parker who came about and then formalized the concept of the geometric tolerance. So there are slight variations in the story, but nonetheless, what we are interested in is basically how is it that we apply the geometric tolerance, and then how is it that we're going to be using it in this case. So between the previous standard and the current standard, so the latest one is 2018, so ASME Y14.5, 2018, and there is kind of like a slight variation from the previous example. So there are basically geometric tolerance. So it has tolerancing symbols. So there are basically 12 symbols, and then we have the tolerancing value. So so symbol specifies what is it that you're trying to control. The tolerance value tells you how much you're trying to control, and we typically optionally have something known as modifiers, and then we also have datum references. So this is just kind of a quick summary, and then we will see as we go along what is it that we actually mean in this case. So let's start looking at some of the, or actually we look at all of the geometric symbols, but we'll focus on a few of them initially. So the first symbol that we're going to be looking at is known as the flatness. So if you basically have a plane surface, so you can imagine what the flatness means, right? So essentially it's twisted this way. So this is kind of the waviness. So if I happen to look at the surface on the edge, so I'm thinking about how flat is it going to be? Is it going to be like bumpy, or what's actually going to happen? So if you look at the corner, so I'm basically saying essentially this is the flatness, and then what we do is we basically take this plane and then bound it between two parallel, theoretically flat surface. So essentially you have this wavy surface in the middle, and then you kind of like keep moving the planes closer and closer till you're fully bounding the surface. So once you do that, so you can measure what the gap is going to be between the two theoretical planes, and so that's going to give you the flatness tolerance. So it's going to basically be like what is the distance between two perfectly flat planes that will completely bound the plane in question. So that's the concept of flatness. So the symbol is the parallelogram over here. So essentially what does that mean is that we are bounding the plane between two theoretically flat surface, and then if the tolerance is 0.01, then so we're basically saying all of the variation that's happening needs to be within tolerance bound that we basically specify. That's what is meant here. So at the bottom of the page, we have an example. So what I'm going to do is I'm going to assume that I'm making the back or the bottom surface, so the surface that you can't see, to be flat. So I can imagine kind of like my arrow going behind, and then I'm going to make that flat, or that surface flat. So obviously I can't, already you see the problem, so I can't basically put a label on this front view over here, simply because I don't know if I'm referring to the top or the bottom. So what I need to do is pick the perpendicular view, or we apply or kind of denote the tolerance on the I think I misspelled this. So the transverse view, SE is missing. So basically on the perpendicular view over here. So we basically need to pick this view over here, and that's where we're going to apply our tolerance. And so typically what we do is we draw a leader plus a box. So I have a leader. So typically you can have this leader actually start at the surface, and then we draw a little bit box. So here is where I'm going to provide all of the information regarding the torque. So I have to basically convey two pieces of information. So the first one be, what is it that you're trying to control? That's going to be the flatness. And then I'm going to convey what value of tolerance I need to specify. So I basically have two pieces of information. So what I'm going to do is split this box into two parts. So that each one is known as a frame. So we split the box into frames and then add the tolerance symbol followed by the tolerance value. So this is going to be, so if I did that, so that's going to be basically the flatness symbol and then the flatness value of 0.01. So since we have basically denoted a theoretical flat surface, or rather we have provided a tolerance, the theoretical flat surface basically can now be used as a reference for future dimensioning. So we are basically going to call it as a datum. So essentially, so you have these two theoretical surfaces, right? It doesn't matter which one you pick. So these are going to be a reference datum. So typically what will happen is you will basically say, I want to have the bottom surface to be flat, and then you lay it on the bottom. And so that bottom reference becomes the datum that you can use. So we're going to label it. So what we do is we put a filled triangle. So this is a filled triangle, and then you have a little arrow, and then you put a box, and then you can give it any name you want. You can call it Steve, but that's not going to be very useful. So we basically start with the letter A, and so we call this to be a datum or datum A. So once we do that, this is basically finished our flatness tolerance. So we can, or there is another way you can denote it based on how much space you have. So what you can actually do is you can kind of essentially put an arrow mark instead of the leader. So essentially you can have the same thing, put an arrow mark and then attach the tolerance to the arrow mark. So that's one way of doing it. And this label over here, you can also add the label and attach it to the tolerance notation over here. So the other way to do it, and then you can basically attach it like so. So either this goes over here, or basically this A would go over here. So that's what we basically do with respect to the flatness tolerance. So the next tolerance we're going to be looking at is the perpendicularity. So what do we mean by things being perpendicular? So they're basically at 90 degrees. So essentially I've defined my theoretical flat surface that we initially had, and then I'm going to have another surface that's going to be perpendicular. So the perpendicularity kind of also incorporates any twist that you have, any potential angle that you're going to have in the surface. So when you say perpendicular, you always are going to be saying perpendicular with respect to. So it doesn't really make any sense when I say my line is perpendicular. So that doesn't really have any reference. So the question is it perpendicular to a line here or another line somewhere else? So that's, or same thing happens with the surface. You want to always say it's perpendicular with respect to something. So we want to make this surface to be perpendicular. So what does that mean? So I pick, say for instance, if I pick the surface, it's going to have a wiggliness to it, right? So what I'm going to do is I'm going to define my reference surface. So typically that will be the bottom surface. That's what I'm going to make it perpendicular to. And then this is going to be a reference. And then I'm going to draw two planes which are exactly perpendicular to my reference direction or reference plane. So then the tolerance is going to be the distance between the two planes. So I can, if I want to specify the tolerance, I'm basically saying if I have these two perpendicular planes, I want to make sure that any variation that happens either in the waviness of this plane or the plane not being straight, all of it needs to fall within this tolerance value of 0.01. So the symbol for perpendicularity is this perpendicularity symbol, and in the GD or GD&T context, we have to basically specify a reference. So this reference here needs to be specified when you're basically specifying this perpendicularity tolerance. So let's look at the example. So then what we need to do then is define a flat surface to begin with. So let's look at this example. So I'm only looking at one view here. So I'm going to basically make this surface to be flat first. So we need to apply the flatness to the bottom. So I'm using a slightly different variation. So instead of having the leader, the arrow mark, so I'm calling the bottom surface, or denoting the bottom surface needs to be flat within a tolerance of 0.0. So here I'm going to label the surface. So I need to add a label. Call this A. This is exactly the same thing that we did in the previous flatness example. So once we do that, so now I can make this surface to be perpendicular to the bottom surface. So the way I do that is we basically would add the new frame. So here again, so it could an arrow mark or a frame like so. And this is a little bit longer because I need to put 3 pieces of information over here. First one is going to be the symbol. So you divide this, put the symbol and the tolerance. So this is very similar to what you did before. It says perpendicular within 0.01. Right. So now I need to tell you what it is perpendicular to, and so that's where the datum comes in. So essentially we are extending the frame, or basically adding one more, essentially one more box there, and then we say it needs to be perpendicular with respect to A, and then for good measure we can actually label this to be B. Again, I can put the label on the surface, or I can attach this the tolerance here. So either one would actually work, and so this is basically how you would specify the perpendicularity. So what we basically dealt with is the flatness and the perpendicularity of the surfaces. So next we're going to be looking at what's known as the circularity circularity tolerance. So the symbol for the circularity tolerance is just a circle like so. So what does it actually mean? Is we typically, so for instance, if you have this drawing over here, so it specify the circularity tolerance like so. Essentially put an arrow mark and then say put the circle and then 0.01. So this doesn't really have any reference or a reference to it. So what does it actually mean is essentially if I take any cross section of this cylindrical surface, so typically if you're manufacturing a part, it's going to have a 3D form, right? So essentially you take any cross section and then any variation that is there in the cross section needs to lie within these two theoretical circles. So essentially if I take a cross section and the cross section happens to be here, so I use kind of like maybe like a profile measuring device or a 3D contour measuring device, and I find the profile to look like this. So what I want to do is bound it between two theoretical surfaces or two theoretical circles, and then the difference between the two circles, so the radius difference would be 0.01. So basically this distance needs to be 0.01. So then just a quick note, the circularity is essentially applied to each cross section of the hole. So essentially even if your hole is a little bit wiggly, so then you're applying the circularity each cross section. So we can actually extend this concept of circularity to a whole cylinder. That's where the cylindricity comes in. So the symbol that we use is kind of basically the circle with two slashes on either side. So we're going to have slash and within 0.01. So what we're doing again is just as we previously bounded a circle between two theoretically perfect circle, for the cylindricity, we're going to take our cylindrical surface. So imagine this really jagged cylinder is what has been given to me. So I'm going to try to bound it between two theoretically flat surface, two theoretically perfect cylinders which are concentric, and then the distance between those two theoretical cylinders needs to be given by the value of the tolerance. So in this case, the difference in their radius would be 0.01. So the next concept we are going to be looking at is known as the parallelism. So which is kind of the symbol is going to be the parallel symbol. So essentially we again have this parallel within 0.01 with respect to the reference A. So if you imagine the previous example that we did, so that we just completed. So what I can actually do is I can say the top surface needs to be parallel to the bottom surface. So that's what we can do in this case. So if we come back, so essentially we're coming back over here. Um, so then what we do is we're basically saying that so we basically would draw two theoretically flat surface that's parallel to the original surface, and you're going to bound that within 0.01. That's what is meant by um, the, the tolerance over here. So now we are going to basically be looking at what's known as the true positional tolerance, and we're going to be spending a little bit more time, or actually considerably more time than we did other tolerance. So it's because it's a little bit more interesting, and this is one of the tolerance you would end up using more often in your dimensional or your geometric drawings. So just firstly, so what is it meant when you say true position is that we're basically when I say true position tolerance, so again it's the most widely used. So this is used for both locating as well as positioning circular features, also providing the bound on the geometry. So it controls both the location of the cylindrical center, the center of the cylinder, and so what we're basically doing is we're also controlling the other orientation or the axis. So essentially what we're doing is if you basically say the true position, so if this is my cylinder, so I'm actually ensuring or kind of like uh, tolerance on the location, so that's the true position, and then also kind of the orientation and as well as the potentially kind of like how the whole axis actually changes. So you're actually controlling multiple things at once. So then we're basically also controlling kind of the cross section variation here. So this is typically used for holes, but you can also use it. So in the example I gave, it was basically for a cylinder or a peg that was sticking out. So you can apply the true positional tolerance in this case. So in this case, what we're essentially doing is if you have multiple of these, we can actually ensure by applying all of them are located in the position, you can ensure proper assembly. And you can also have multiple holes, and then there is basically no additional tolerance stacker that comes in because you've applied a true positional tolerance. So without further ado, so this is a symbol. So this is full size symbol that we use, and so this is what is going to be done for the true. So we'll actually see how this is actually implemented using the example that we. So let's shift to the document I have here, or the document camera here. So we'll kind of go over the usage or how is it that we'll actually set up the tolerance. So just a quick note. So I'm assuming normally when you're doing the part, so you would actually do the dimensional and geometric tolerance. So I'm going to skip on some of the dimensional tolerance just to make it a little bit quicker over here. So let's do that. So before we do that, we need to figure out where the center of the circle is located, because you're going to give the true position of the circle. It appears to be about 110 millimeters, right? So this is kind of where the center here is. So I'm going to draw maybe like a faint line. And vertically, rather, let's do it horizontally again. line over here. What I'm going to do is I'm going to create my center axis here, and then use that for my dimension. So I'm going to go one long line, short lines in this, and then we do the same thing vertical direction as well. Have one long line and then short lines. So this doesn't appear to be very symmetric, so we can measure what this is coming out to be. Made it 14 millimeters on this direction, and this is 17.5. So we're going to basically give the location of this feature. So this is 17.5 and 14. So I'm going to dimension with respect to the edge over here. So this is going to be 20. So I'm just going to put it faintly in pencil, just rather this was actually 17.5. I'm going to put this faintly with my pencil. So that I know how it is and then use it for a later point. So 5, and this was about 14, that as well. I'm going to put this faintly in. I might need some space for actually going other dimension. So we can actually add the other dimensions as well. So this was, if I measured it correctly, 40, 30, and 20. So we can actually really quickly add those dimensions. So this is going to be 40. So I'm going to just give a little bit of 40. And then if you want, we can use convention that we previously used. It's going to be 40. And this is 20. Then we can give this. So we have these dimensions. So this one, I haven't actually put tolerance as of yet. So the reason is we are going to basically kind of specify the true position of the hole here, right? So we shouldn't actually put the tolerance over here. So here, maybe I need the arrows on the outside. And probably arrows on the outside here as well. Five. So once again, just keep in mind that I haven't applied dimensional tolerance here because I don't want to confuse the true positional tolerance that I'm going to be setting up shortly. So once we have this, so let's do the actual geometric tolerance. So for instance, I already have a leader here, so I can kind of like steal this to kind of create my tolerance here. So I'm going to kind of write some of the nodes here, but you can actually use the bottom of the page to create more of your nodes. So this just, I don't want to zoom in and out of my drawing over here. So what I'm going to do is basically, so we have basically created the dimensional tolerance. It tolerance, except for the location of the hole. This is taken care of. So the next step is to actually create our the datum references. So we basically done this. Datum. So typically we do the bottom and maybe one of this side or this side and then the back of this part. So let's do this here. So I can either, again, so I can either do an arrow from here, or since I already have the leader from my dimension, I can kind of attach my tolerance frame to the reference here as well. So let me just do an arrow in this case. We're going to go arrow. It's okay if the arrow actually crosses the line here, but if possible, you can avoid it, so that it will be helpful to attach it to reference dimensional leader over here. So we have here, and this is going to be parallelogram, which is symbol for the flatness, and then tolerance 0.1. That's what we get, and then we're going to label this as A. Have basically created our first reference. So let's do the second reference. So here I'm going to just borrow this leader here, and this is going to be perpendicularity symbol. And then again within a tolerance of 1. Again, so I'm just picking 0.01 as it's convenient. So your tolerance would, your actual application might depend on the actual application. And this needs to be perpendicular with respect to A. Then we close this frame. So this is here, and then we can call this B. Call this B. And then let's do C, which is going to be this here. So again, I can do, because it makes sense to do the arrow here. Perpendicular tolerance of 0.1. And then I'm going to make this to be perpendicular both to my reference A over here and then the reference B, because this is the third surface. Perpendicular A, So that's that. So notice that I'm not actually going back. Actually, once I call this, let's call this C. So once I call this C, I'm not actually going to go back and add C to here because it basically becomes like a circular reference. You always only have the reference to the previous sizes or previous locations over here. All right. So this is kind of like the standard stuff that you've been doing so far. So now what we're going to be doing is actually going into the true positional tolerance. So that is going to be here. So first I need to add the dimensional tolerance. So this was 10 plus minus 1. And then I'm going to put my tolerance frame at the bottom. Two position symbol, which is bullseye. And then we're going to go within a tolerance, and then we're going to basically go a diameter here, 0.01, and then we're going to use the letter M. Then we're going to go ABC. So I'll kind of make a note of what these actually mean, but we'll kind of go over this order over here. So essentially what I'm saying is I have a cylindrical feature. So this is big, but then imagine this is a hole. So I'm going to basically choose the perpendicular frame. So the axis needs to be perpendicular to a frame. So that's going to be A. So this is always perpendicular axis. Then this one is for the XY location. Those would be the secondary references that we do. So this is known as a primary reference. So the letter M is one of the modifiers. This case is known as MMC. Maximum material condition. So this is the maximum material condition modifier over here. And then what we're basically doing is we kind of like explain what this concept is in just a little bit. This basically specifies that you're basically enforcing the tolerance only at the maximum material condition. Again, I have a little bit more discussion later on. So then we've done all of these so far. We also have an other modifier which is not used here. So L is for least material condition. Then we haven't actually used this modifier over here. So we are not using this here. So we'll talk a little bit more about this later on. But coming back to this dimension over here, so keep in mind that if I don't specify any tolerance, I automatically, or the manufacturer would automatically take the default tolerance for your drawing. So we don't want to do that. Then what we want to do is tell the person that he or she shouldn't actually use the default tolerance. So the way we do that is we use what's known as a basic tolerance. So we need to basically tell basically part of a little bit confusing. Just use two different sheets, that's okay. So then what we do is we use what's known as a basic tolerance. What we do is we basically have a box around the number. So this basically means do not apply default tolerance. Right, so what we do is in this case we put a box around these numbers. So what this does is tells everybody that you know what, do not take the default tolerance, and so this basically means that there is no implied tolerance that's associated with the drawing over here. So that's what is putting the box over here. So I'm going to discuss a little bit more about the MMC and then what all of these mean, but we'll kind of quickly go over the basic steps that we did. So we quickly applied the dimensional tolerance for the part, and for the location of the hole, because I'm using the true position, which controls both the axis and kind of the orientation and all of those features, I want to ensure that I don't actually apply a tolerance here. I didn't apply plus minus values over here, and to kind of like enforce the fact, I basically put a box around it and then call it a basic dimension. So that's what we did here. So we created the dimension and then we did this. In order to give the true position, so for instance, if I want to give the position of this cylinder over here, so what I need is I need the XY location, right? So this is a cylinder, so it can move anywhere in the plane, but it's a 3D surface, so it can also kind of like rotate in this plane. Although it can move up and down, that's not a concern here because you're not really assuming the whole kind of like jumps out of the part, right? So you're not really concerned about the Z direction or the out of the plane rotation movement, but what you're really concerned is the orientation of the hole. So in order to control all of these, essentially, or more precisely control the axis of the cylinder, what we first do is we basically need to define three axes. So the first axis is known as the primary datum. That's going to be what goes in here. So that tells you the plane to which the axis is perpendicular. So that's going to be the bottom plane. In this case, this is the primary reference. So my axis will be here, or in this case, the axis will be coming out of the plane here, or basically coming out of the plane. That's the primary reference. And then the secondary reference B and C can be in any order. So what you're basically saying is in this view, I'm going to kind of like ensure that once I define left side plane, the back side plane, so I can basically locate the axis with respect to those two planes. So essentially we are fixing the orientation with respect to the bottom plane. So that's basically perpendicular, and then we are basically specifying all of these. And then what you're basically doing is I'll kind of explain what these are. So instead of giving a linear tolerance, you're actually providing a circular tolerance for the hole. So that basically means that instead of having like a x or a linear distance for your tolerance, basically draw a particular circle of this diameter. So kind of explain why that happens or what that means. And the letter M is known as a modifier, and then we're basically saying that this whole geometry is only being enforced at the maximum material condition, or MMC. So let's kind of come back and then see what is it that actually what we actually did, or what did we actually specify here. So here I'm just assuming I have this cross section of the hole here, and then what you're doing is we're basically looking at, see, each cross section of this hole, and then we basically can bound all of this cross section within some range over here, right? So imagine I pick one here, that's the center, this here, this is the center, and then bottom here, this is. I kind of do all of this for all of the cross section. So then I collect all of these centers. Again, so I have space below the paper, you can note down. but I wanted the figure side by side, so I'm doing notes here. So here, so again, all of these circles needs to be bounded between 10 plus minus 0.1. That's denoted by the dimensional tolerance. So once we collect all of these, so what we do is we're going to assume that we can collect and then put all of these on the axis inside some cylinder. And then what you're doing is that we're specifying some tolerance on this curve of the centers. So based on what we've done, so we're basically saying that all of the centers need to lie within a cylinder of diameter 0.01, or if you specify 0.05, so it will be 0.05. So the theoretical cylinder here that needs to be perpendicular to my reference A, then the true location of the cylinder is denoted by my references B and C. So that's how we will come up with this. And so this, what we do is when we apply the MMC modifier, so we're basically doing all of this when the each of this cross section is at the maximum material or 9.9. So the maximum material condition for a hole is when the hole is smallest. So we put the symbol, so this would be basically 0.01 over here. So again, have a space at the bottom that you can fill in here. So the next page, so this is showing only half the page, but and then you have the rest of the half page here. So what you're basically going to do is I would like you to kind of pause the video here and then do the exercise here. So what you're going to be doing is I'm telling you that I had somebody manufacture all of these parts. So all of these are referring to the same basic size and the dimensional tolerance. And so what you're going to do is you're going to basically work out the potential tolerance here. So you're going to basically variation in the size cross section that will give you dimensional tolerance, and also the variation in the center axis, which will give you geometric or the true positional tolerance. So assuming all of these are located at a particular point. So again, I'd like you to pause the video here and then complete this problem in. We'll continue the video actually. So welcome back. So I've basically just rearranged my drawing into one sheet so it's easier to follow. So here, so if you look at this, so what I'm going to do is essentially mark off at each like multiple cross sections. I'm going to pick maybe like 5 of these, then mark off the center axis over here. So then what is going to happen is I'm going to mark off these values. So maybe 5, and then we go mark the centers over here, and then we can measure the dimensional and geometric tolerance over here. So if I look at all of these, so you'll notice that so this first one is basically varying between 20 and 20. So the second one is between 22.5 and 17.5 over here. So this one is 20 here and 20 all the way. The third one, actually fourth one, is 22.5 over here and then 17.5. So it varies between those values. And the fifth one over here is 22.5 all the way. So now if I want to find the geometric tolerance, so what I can do is connect all of these centers and then find out how wide this band is. Again, I need to be careful that I do only in this range over here. So if I do that, I can draw 2 parallel lines and then see how they actually measure. So obviously if I drew 2 parallel lines, it doesn't make any difference for the first and second case. So those would be 0, and the second one, if I measure, that comes to 5. The third and fourth, the third, fourth, and fifth are actually this is going to be 5 millimeters. So if I take a closer look, so this would kind of be the ideal case for my drawing, and then this would be only dimensional change. So this one is maybe only geometric change, and this one is a combination of both. And the final one is where all of the peg, in this case I'm assuming it's an external diameter, is at the maximum size or maximum material, and then there is a geometric tolerance of 5 millimeter. So when you're putting this together, my dimensional range is between 17.5 and 22.5. So I could have had this at 20 plus minus 2.5, and my geometric range or geometric tolerance is a circle of diameter 5 millimeter. So now let's look at only the last one where everything was the maximum material condition. And just to illustrate, so I've basically drawn some lines over here. The top one is overall diameter, and then the middle one is kind of the variation. So notice that I can actually put both of these together, and whole thing actually fits within this diameter. So essentially the bounding box, or the bounding cylinder in this case, will be the MMC diameter of this peg plus whatever geometric tolerance is left. So the next page I've actually left for you to be blank, so you could have filled in all of your notes over there and then do the discussion for that particular case. So just to kind of like summarize, the reason we did this exercise is to kind of get a better feel of what geometric and dimensional tolerances are, and then how they could potentially interact with each other. Just a quick word of caution. I basically blew up all of the dimensional and geometric tolerance values so that it's actually easier to illustrate the concept and for you to actually put all of these together. But in actuality, those values will be much smaller, and you probably cannot use a ruler to make the actual measurement. But nonetheless, it still illustrates the whole purpose of what's actually happening. And the other thing we notice is the worst case scenario. So if you're trying to maybe like put or mate surfaces together, is when the peg is also very large, and it's kind of like varying the geometric variations also the maximum. So that's when the envelope becomes the largest, and that's the reason that we enforce, or say that we are enforcing the tolerance at MMC. Then it means that any other condition, the assembly would still be possible. So that's the reason we add the MMC modifier, or enforce the tolerance at the maximum material condition. So next, we have a couple of, or rather one more example over here, so which actually works out to be two examples. So what we have here, or what I've drawn here, is a set of circles over here. I have multiple circles, and then what I've done is I have everything, all of these circles are exactly 50 millimeters, or the circles over here. And then what I've done is I've kind of like varied the center of these circles all over the place. And then imagine you're basically kind of peeping into the hole like so, and kind of like and then looking in, and so, or rather maybe like a telescope, and then you're seeing what is going to happen. So you can think of this in one of two ways. Either you're looking into the hole, so where you'll be looking at the inside of this region, or if these are external features, you're basically looking at the external diameter. So what we're going to do here, or you're going to do, is basically find the geometrically calculate the inside diameter, which is known as the inscribing circle, or the largest in circle or largest inscribing circle, and then also measure the largest circumscribing circle, and then note down the values, and basically make a note of these values, and then we'll just compare notes. So here's what we do. So for instance, I'm going to just use a screen ruler over here. So what I'm going to do is use and then try to fit a ruler here. So we did that. I'm going to start at 0. Then this comes to 45. So I'm going to note down the largest inscribing circle, 45 millimeters. And then if I did the same thing, so I moved the ruler to the outside. This comes to 50. You can actually check that the same thing works if I do it vertically or any other direction. So this is actually 55 millimeters. So basically for an internal feature, the bounding cylinder is going to be MMC diameter minus the tolerance diameter. And then for the outer feature, if I'm looking at the outside, so that's going to be MMC diameter plus the tolerance that we have. So that's what we did, and then we can figure out. So then the idea is, if I basically have an internal and an external feature, I can kind of calculate the bounding box for my internal feature, and then bounding box for the external feature, and then make sure that the bounding box for the internal feature is always smaller. Then I can ensure that the two parts are going to be assembled together. So this is conceptually what you can do, and normally it might be a little bit different because the tolerance might be very small, so you might be able to like force fit it based on the size that you have. But if you want a lot of precision, so you might need to take care of all of this. So let's look at the few final tolerance symbols that we didn't cover. So the first one, or actually this is number 8, is not going to be the straightness. So this is typically kind of given as the straightness of the axis. And you can also do the straightness of a plane where you're basically looking at linear direction, but not to that extent. Flatness is typically more commonly used. So the next one we're going to use or look at is known as the angularity constraint. So this is kind of a generalization of the perpendicularity constraint. So imagine you have a line or a plane that looks like this. We have a reference here, and then what you do is you have plane. So the angle would be, say in this case, about 60 degrees. So that would already be given to you. That will be the theoretical value, and so there is no variation applied on it. And then you basically have a tolerance zone, and then you the value over here. So number 9 is going to be profile of a line, or rather, excuse me. So this is going to be perpendicular, and then we use a datum here. Number 9 is going to be profile of a line. The symbol is kind of a semicircle over here. So this requires a datum. So if you have a line feature, say, so theoretically I've drawn the line and given you all the dimension. For instance, it's kind of like a spline that you drew and given all the values, and then you say, hey, I'm going to accept this variation on top of it. And then the next one is profile of a surface, which is kind of a extension of the profile of a line. Rather, you can have a surface which is maybe actually wanted, say for instance, want an aerofoil surface for wind turbine. So then you can actually give a profile and then give a tolerance on the profile of on the surface. So you might basically have cut off and then kind of give the profile here. So number 11 is circular runout. So I have a little cartoon over here. So generally the circular runout is kind of used to define variation or the waviness of a surface with respect to another circular feature. So the symbol is going to be this arrow here. So for instance, if I have this circular feature, and so this is actually applied to a circular feature with respect to a circular feature. So imagine you have this part here, and then I'm going to be rotating it as such in this direction, and then I'm going to basically maybe use like a tool here and then see how much this surface actually wobbles or varies. So kind of maybe this has a profile here, and so then we bound it between two theoretical circles and then give the distance between the two. So the circular runoff is for each cross section, and then the total runoff is the same concept being extended for the whole surface. So this would instead of this being a circle, you basically use cylinders and then do the total runoff. So there are two other symbols that used to be used in an older version, which are now no longer being used in the 2080 version. So actually ignored them over here. So this basically brings an end to our brief introduction and kind of conceptual discussion with respect to geometric tolerance. So we'll actually have a follow-up video, SolidWorks implementation of tolerance. But nonetheless, so what we actually covered was the concept of geometric tolerance, essentially kind of controlling both the length and then kind of the shape. You're okay, maybe it twists a little bit, the ruler twists a little bit, that might be okay. But you might need to specify a particular limitation or limit or a tolerance on these variations in the geometry based on your particular application. So based on the geometry that you have different geometric tolerance that you can actually apply. So typically we define most of our tolerances to a starting primary flat surface, or basically use flatness as a reference, and then we kind of build all of the other tolerances. Want to make perpendicular first reference theoretical flat surface, then you can do the same thing for true position. So the true position I mentioned is the most commonly used tolerance. So that basically kind of, if you have a cylindrical feature, a hole or a peg, control both where the peg is going to be located on the xy plane, as well as kind of the orientation, as well as the twist and the variation of the axis by specifying three datum. So the primary datum is always going to be perpendicular to the axis of the cylinder. So if I call the bottom face to be D or C, so then my first reference for my hole is the C or the D that I chose here, and then the other two would be ones that locate the location. once that give the location. So we also looked at what it means with respect to geometric and dimensional tolerance and how they can put it in fact, and then we can see how they actually sum up, and then we basically looked at the effect, axiometric condition, and how the bounding box and the bounding cylinder calculated, and then we finally concluded with looking at few example. Actually, we looked at the other tolerances that are basically used, and there wouldn't be like a drawing question on those, but nonetheless I can have a multiple choice question that be asked in there. So this basically concludes our video, and thank you for watching. So I'm going to just have a follow up with the SolidWorks video. Thank you.